Welcome to the 19th lecture in our course on quantum mechanics. With this lecture, we're starting section 4 of our course, in which we will explore a contemporary topic in quantum mechanics research: quantum information and quantum computing, my own field of research specialty. Our question is, how can we use quantum systems to store, retrieve, transmit, and process data? How can we use single photons, electrons, and atoms to perform our tasks? We're going to ask, what are the limitations imposed by quantum mechanics? And we'll also ask, what are the opportunities that quantum mechanics affords? However, this is not really a question about futuristic technology. It might be fun, it might even be useful to build a quantum communication system or a quantum computer, but we are interested in another aspect of the subject, a deep question about nature. Rolf Landauer, who was a physicist at IBM, said it best. He said that information is physical. There's no such thing as disembodied information. Information is always represented by the state of a physical system, by ink on paper, or electrons or photons, and so on. Similarly, there's no magical information processing. The computation in a real computer is always a physical process. It always follows the laws of physics. So that leads us to two profound questions about the nature of quantum physics and information. And the first one is, what does quantum physics tell us about the concept of information? And the second is, what does the concept of information tell us about quantum physics? Now, the concept of information is somewhat familiar to us these days. We live in the information age. We're familiar with telecommunications and optical and electronic storage media and computers and so on. And so basically we already have a concept of information, although we'll need to discuss that concept. And that concept is basically what we'll call classical information. That's the information that can be stored in macroscopic systems. It's our familiar idea of information. It's the information that could be in a book, the information that could be in a movie, the information that could be in a musical recording. The amazing thing is that information can be changed from one physical form to another. Let's take as an example this lecture. There's light and sound here in our classroom. But then we have that information turned into electrical signals in the camera and the microphone. Those are recorded as magnetic patterns on a videotape. You may have received this lecture in the form of tiny microscopic dimples on a DVD. That DVD is read by reflected laser light in a DVD player. It's turned into electrical signals again. And finally, right now, it's light and sound again. All of these transformations of physical form, yet the same information through all of the transformations. A remarkable fact. A remarkable property of information. Now, the basic unit of information is the bit. One bit is a binary digit, a 0 or a 1. And that 0 or 1 can stand for yes or no. It could stand for on or off. It could stand for left or right, etc. So how do we understand bits? Well, let's take, for example, the game of 20 questions. In the game of 20 questions, you're supposed to guess a word by asking 20 yes-no questions. In other words, in the course of the game, you get to learn 20 bits of information. 20 yes-no answers. So is 20 bits of information enough to guess the word? Well, how many different combinations of yes-no questions could you get? So yes-no answers could you get in the course of the game? We could get two different answers for the first question, two different answers for the second question, and so on. So the total number of possible combinations of answers is 2 times 2 times 2 times 2, 2 to the 20th power, which is about 1 million. So you ought to be able to identify any of 1 million different words with 20 yes-no questions, if you're clever. Turns out that this is not far from the actual number of distinct words in English, especially if you leave out some of the very unusual words like syzygy or something. If you play 20 questions with somebody who picks syzygy, you're in trouble. So you could hope to win at 20 questions, but it isn't easy. And that's exactly why it's a fun game. And it's helpful to remember the result of this calculation. An English word needs about 20 bits of information to represent. Okay, we can use different physical systems to represent bits. We mentioned some of the physical manifestations of the information in this lecture, for example. And any sort of information can be recorded, encoded in a series of binary digits, a series of bits. And we can use bits to measure how much information something contains by asking how many binary digits, how many zeros and ones do we need to represent that information. So how many bits do we need to store a novel? How many bits do we need to store a nice photograph? How many bits do we need to store a minute of music on a digital music player? And it turns out that all of these are about the same. All of them are about 8 million bits, or 1 megabyte. And that's the amount of information that those different kinds of information contain. Okay, so much for classical information. What about quantum information? Quantum information is the type of information that can be stored in a quantum system. And we can transform the physical form of quantum information, just as we can transform classical information, using our rules for quantum mechanics, following our update rules 1 and 2, depending on whether or not there is a measurement or not. And the basic unit of quantum information is called the qubit. Now, a qubit is a system, a quantum system, that has 2 basis states. And we've seen a couple of examples already. The photon in an interferometer was a qubit. It had 2 basis states, upper beam or lower beam states. The spin 1/2 particle was another example of a qubit. If we measure the z component of spin, we got basis states up and down, spin plus 1/2 or minus 1/2. So a qubit is just any one of these, any quantum system with just 2 basis states. And we could call those qubit basis states 0 and 1 if we like, the ket 0 and the ket 1. But if the only thing there were to qubits were basis states, then it would just be a bit. It would just be another kind of a bit, or classical bit. So there's actually more to a qubit. Because of course, in a qubit, you can have superpositions of the basis states. You can have a funny combination of 0 and 1. You would represent that by a state A times 0 plus B times 1, where A and B are amplitudes. You can have a superposition of 0 and 1. You can't have that for a classical bit. Similarly, if you have more than 1 qubit, they might be entangled together. That's another possibility. So qubits are much richer. Qubits are much more complicated and subtle and interesting than ordinary bits. But of course, we could use qubits to send classical information, to send bits, if we like. So to explain this, I'm going to introduce you to our 2 protagonists, Alice and Bob. By tradition, Alice and Bob are the heroes of quantum information theory thought experiments. Alice and Bob are the characters that carry out our thought experiments. And so we'll just mention Alice and Bob, and they'll show up quite often. Sometimes there will be other cast members, but the stars of the show are Alice and Bob. And so in this thought experiment, Alice wishes to send Bob a 1-bit message, 0 or 1. That might stand for a very important piece of information, yes or no, on or off, left or right. So she wants to send it by using a qubit, say a spin 1/2 particle. So what does she do? She prepares the spin of the particle. If she wants to send 0, she prepares it spin up. If she wants to send 1, she prepares spin down. So 0, 1, up or down, yes or no. So the particle then is sent to Bob. And what does Bob do? Bob measures the z component of the spin. And that allows him to read the message because he can tell whether the spin is up or down. If Bob were foolish enough to do something else, like read the x component of the spin, he'd lose the message. But he can read the message by reading the right variable. But you know, Alice notices that there are more than just 2 quantum states available. In addition to the 0 and 1 basis states, the up state and the down state, there are lots of other states. So she gets the idea that maybe she could send 2 bits of information. If there are 2 bits of information, there are 4 possible messages. That's 00, 01, 10, and 11. Those are the 4 possible 2-bit messages. So Alice tries to encode, let's see, she encodes 00 as up, and 01 is down. But 10 is encoded as spin to the right, and 11 is encoded as spin to the left. So that's great. She has a quantum state for each of her messages, and so she prepares the spin in the quantum state, and she sends it to Bob. She sends the spin to Bob. Bob doesn't know what her message is, but he's going to try to figure it out. Can he read her message correctly? And the answer is no, he can't. I mean, Bob can tell up from down with a z measurement. He can tell right from left with an x measurement, but no measurement will allow him to distinguish all 4 of these spin states. So Bob can't read the message that Alice sends. The moral of the story is that the capacity of a qubit for sending classical information is just 1 bit. You can put a bit in a qubit, but you can't put more than a bit in a qubit. Okay, can we do the reverse? Can we send qubits using bits? Well, that's a complex question. I'll just tell you that it depends on what you mean by that question exactly. You have to be very careful. And at worst, the answer is no, you can't send qubits by bits, no matter how many bits you use. And at best, it requires a lot of bits to send 1 qubit. I mean, after all, to describe the superposition state A0 plus B1, you've got to describe the amplitude numbers A and B. And to describe 2 numbers to sufficient accuracy, it may take you many, many bits. So just in general, there's no easy way to send a qubit using only bits. Now, let me tell you a little story, a personal aside. I can tell you the origin of the term qubit. I can tell you because I was there at the exact moment. And this happened during a conversation with the quantum physicist William Wooters from Williams College. He and I were in a car driving on our way to the airport in May of 1992. And we were discussing some problems we'd been working on about information and quantum physics. And as a joke, we proposed that maybe we need a new unit for specifically quantum types of information. And we said, oh yes, we could measure things in qubits. And we thought this was amazingly funny because, of course, a qubit is a unit of length in the ancient Near East. And so Noah's Ark in the Bible is 300 cubits long and 50 cubits wide and 30 cubits high. And we thought it was just a hilarious thing to measure something in physics in qubits. But then over that summer, I thought a lot about qubits. And I decided that qubits was a good idea. So in the fall, I introduced the term in a talk at a conference. And it's now a standard scientific term. But just between you and me, it started as a pun. Okay. What is the fundamental difference between classical and quantum information? Physically, what's the essential distinction between them? And the answer is really interesting. The answer is copying. We can always, in principle, copy classical information. We can always, in principle, make a duplicate of it. And the reason is that observing a classical system, like a DVD, for example, observing a classical system need have no effect on it, need have make no damage to the DVD. And if we measure our bits very carefully, we can duplicate them exactly. We can make a copy of the DVD. And that's a serious issue because the copyability of classical information is a problem for copyright law. It's a problem for intellectual privacy law or property law. It's a problem for privacy. How do we prevent unauthorized people from copying information that they shouldn't? It's a terrible problem. But in fact, we cannot always copy quantum information. Quantum information is different. Quantum information is not copyable. Okay, let's see if we can understand this a little better. And I want to understand it by imagining a device. We're going to call this device a quantum cloning machine. It takes a single qubit as its input, and it produces 2 qubits as output. And the output is such that both qubits are exactly in the same state as the original qubit input. That's how a quantum cloning machine would work. So mathematically, we would represent that the ket state goes to a ket which is state. It's a product composite state of 2 systems, 2 qubits, in exactly the original state. And our requirement is that the cloning machine should work on any input state. That's the process of quantum cloning. The question I want to ask is, could such a machine really exist? Is such a machine consistent with the laws of quantum mechanics? Super quantum copying machine, quantum cloner. Okay, so suppose we have such a machine that actually works for the up and down states of a spin 1/2 particle. So up becomes up, up, and down becomes down, down. All right, let's suppose it works for those. Well, how does the machine work? Does the machine work by update rule number 1 or update rule number 2? Are there measurements involved in the machine or not? Well, we don't want randomness in our machine operation. We want a definite result. So let's assume, for the sake of argument, that it has to operate according to update rule number 1. In general, we'll have to consider more complicated combinations of the rules, but this is good enough for now. Let's assume that it operates according to update rule number 1. Update rule number 1 preserves superpositions. Now, suppose we wanted to duplicate the state right. The state right, which is s up plus s down. S is our favorite number, the square root of 1/2. So, if we wanted to duplicate right, we would have to wind up with right. And what is right? Well, it's the composition rule in action. It's s up plus s down times s up plus s down. And if you work it out, it's s squared times up plus s squared times up down times s squared plus down up plus s squared times down down. If you want to simplify that a little bit, you can just remember that s squared is 1/2. But it's basically a sum of 4 different basis kets. That's the state we want. But what state do we actually get out of the quantum cloning machine? Remember, the quantum cloning machine applies update rule number 1, and it takes up to up and down to down down. So it's got to take a superposition s up plus s down to s up plus s down down. That's not what we want at all. The 2 output spins are entangled. This is not the product of right and right. It's something else. So the moral of the story is that the quantum cloning machine has to fail for some inputs. It has to work wrong for some inputs. And that means that no machine that operates according to the laws of quantum mechanics can possibly duplicate a qubit. It's an amazing fact that quantum mechanics was over 50 years old before this basic, elementary, and vastly important fact was even noticed. And it was noticed in 1982 when the quantum no-cloning theorem was proved, the theorem we've just mentioned, by William Wooters, our old friend from the term qubit, and Wojtek Zurek of Los Alamos National Laboratory proved it in much the way that we've shown. And at about the same time, Dennis Deeks from the University of Utrecht proved it a completely different way. They proved that a perfect quantum cloning machine is impossible. They proved that quantum information cannot be exactly copied. Let's tell a science fiction story. Really, it's a fantasy story. What if we did have a perfect cloning machine? What if somehow we were provided with a machine that got around this proof somehow, and we could actually make perfect copies of quantum information? What could we do with a machine like that? It's sometimes useful to imagine the impossible and see what follows. Well, one of the things we could do is we could send 2 bits in 1 qubit. Remember our previous attempt, Alice's previous attempt, she sent up, down, right, and left to Bob, each one representing a different message. And Bob had to figure out which one of those he got. And he couldn't do it. There was no quantum measurement that allowed him to do it. But now let's suppose Bob has a quantum cloning machine. So what does he do? He takes the spin that Alice sends to him, and he runs off 2,000 exact copies of it with his quantum cloning machine. So what does he have? He now has one of the following things. He has 2,000 qubits whose state is up 2,000 times, or down 2,000 times, or right 2,000 times, or left 2,000 times. He has one of those 4 situations. So what does he do with his 2,000 qubits? Well, first thing he does is he measures Z on the first 1,000 of them. Now, if the state is up, that means that when he measures Z on those qubits, he'll get plus 1/2 every time, all 1,000 times. And if it's down, he'll get minus 1/2 for his measurement, all 1,000 times. What about the other 2? What if it's right, or left? Well, each one of those has a 50-50 shot. So probably he'll get about 500 plus 1/2 and 500 minus 1/2. So he can tell whether it was up or down or one of the other 2. So how does he figure out what the other 2 are? Whether it's one or the other 2? Well, he measures X on the next 1,000 qubits, and he can sort them out. He'll either get all plus 1/2 or all minus 1/2 or a mixture. And by combining the results of these 2,000 measurements, he can determine which of the 4 qubit states was sent by Alice. So he can read her message. He can send 2 bits in 1 qubit, and that's impossible. Why can a qubit only convey 1 bit of classical information? Part of the answer lies in the no cloning theorem. Now let me tell you an even better science fiction story about what you could do with a quantum cloning machine. I mean, after all, sending 2 bits in 1 qubit is not that exciting. It violates some principle that we had previously found, but it doesn't seem very dangerous. Now I'm going to tell you that if they have a quantum cloning machine, Alice can send a message to Bob faster than the speed of light. So how does it work? Well, let's imagine that Alice and Bob share a pair of spins that are in a total spin 0 state. In other words, they made a pair of spins like this yesterday or sometime in the past, and they now just possess them. They've held on to them. The spins are still in a total spin 0 state. Now, if Alice measures Z on her spin, then we know that Bob's spin is either going to wind up in the up state, or the down state, because his spin state has to be exactly opposite to Alice's measurement result, because it's a total spin 0 state. That's entanglement. And this happens sort of at once. Now, it's also true that if Alice measures X on her spin, then Bob's spin is either going to wind up being right or left, because it will have to be exactly opposite to Alice's measurement result, because it's a total spin 0 state. And this happens at once. Now, ordinarily, Bob would not be able to figure out exactly what he has because there's no measurement that he can do that can tell whether he has up, down, left, or right, that distinguishes those four states that would allow him to sort them out. And anyway, Alice can only control her choice of measurement. She can't control the result of the measurement. That result is random. So she can't really control the exact outcome, and therefore couldn't use the outcome of the measurement to send a message. So it looks like there's no hope for sending information using an entangled pair of particles faster than light. But suppose Bob had a magic cloning machine. Then Bob could do what we previously described, could make a couple of thousand copies and make some X and Z measurements, and he could tell exactly what he has. He could tell whether it was a spin up or a spin down or a spin right or a spin left. And that means that he can determine Alice's choice of measurement instantly. If Alice chose the Z measurement, he'd either be getting spin up or spin down. If Alice chose an X measurement, he'd either be getting spin to the right or spin to the left. And he can find out at once, right away, even if Alice is 1 billion kilometers away. So what does Alice do? Alice represents the message 0 as a Z measurement. If she wants to send 0, she makes a Z measurement. If she wants to send 1, she sends an X measurement. Bob, on his side, makes thousands of copies of the qubit, performs a lot of measurements on them, and receives Alice's message immediately. He can tell immediately which measurement she made. It was exactly this idea, the idea that a perfect quantum cloning machine would let you communicate faster than light, that led Wooters and Zurich and Deeks to prove the quantum no-cloning theorem in the first place, that led them to prove that no quantum cloning machine could exist. And so information could not be sent faster than light, because this particular way, using a quantum cloning machine, is impossible. Okay. We've established that there are two distinct ideas of information, at least. There's classical information, which is measured in bits and can always be represented by bits. And there's quantum information, which is measured in qubits, can be represented by qubits, which are quantum states with 2 basis states, but also lots of other superposition and entangled states. We found that classical information can always be copied in principle. Quantum information, though, cannot always be copied. Quantum information is uncopyable. This is the quantum no-cloning theorem. So that raises an interesting question. The question is, can we use the uncopyability of quantum information to do something useful? Because we said that the fact that classical information is so easy to copy is a big problem. Could we solve that problem maybe by using quantum information? And the answer is yes. Next time, we're going to talk about the subject of quantum cryptography, which is using quantum uncertainty in the service of privacy. That's next time. I'll see you then.